Okay, we're going to pick up where we left off on the last video here. We started chapter 7, which focal point was on what a sampling distribution is. Okay, a sampling distribution of a statistic is the distribution of values taken on by that statistic in all the possible samples of the same size. Okay, so the key here is, and we had sort of demonstrated this with the reaching for beads activity, is you would reach into your population, you would pull out a sample size, I'll just say 10 for an example, okay, and you would continue to do that until you got every possible combination of 10 individuals that you could have mixed together. Okay, that's what a sampling distribution is. Now, it does mention here that in practice, it's quite difficult to actually take all the possible samples of the same size. So normally when we do this, we typically call it an approximate sampling distribution. But just know that an actual sampling distribution is really talking about if you took all of the possible combinations of samples of that same size. Okay, so what we generally do is we usually just use a simulation to kind of imitate this process of taking many repeated samples over and over again. We will eventually learn here a little bit with probability that will help us kind of arrive at the conclusion that we're after without doing a simulation. But it's really important that you are understanding the distinction between a population distribution, a distribution of a sample, and then a sampling distribution. Those are three completely different things. And so let's just break down very briefly here. A population distribution is when you actually have surveyed all of the individuals in that particular population, okay? And it describes what each of those individual observations would look like. You could make a dot plot of it. You could make a histogram like we have here. This is actually representing that reaching for beads activity, where I believe we said half of the beads were red and half of the beads were blue. Okay, so you can see this is just a frequency here. We have 100 red beads and we have 100 blue beads. This is the population distribution because it's showing the counts for each individual in the population. When you move to a distribution of a sample, which is also called just a sample distribution, not a sampling distribution, that is when you are actually coming over to your population and you are simply going to take out one sample. Okay, you're only drawing out one sample. Okay, so this is consisting then of you graphing the contents of that one sample of whatever your sample size is from the population. Again, a sample distribution or a distribution of a sample is just describing the individual observations. So this right here would be an example of a sample distribution. You can see that this is showing that we drew out 20 beads from the population, and it's showing what the contents are of each of those individual observations. It looks like we got 12 blue beads, we got 8 red beads. I think the variable of interest is what is the proportion of red beads in your sample. So p hat would be 8 out of the 20. Okay, that is a sample distribution. A sampling distribution is when we are actually going to take multiple samples. Okay, we're going to take multiple samples. We're going to calculate a statistic and then plot all those statistics. Okay, typically in the fashion of maybe a dot plot or something like that. Okay. So you can see I just have illustrated here two different sample distributions. My second one, note these are the same size. They're both taking out 20 beads. Okay. On the second one, I ended up getting 11 red beads and 9 of the blue beads. So my p hat for the proportion of red beads out of the 20 was 11 out of 20, or 55%. Now, when we move over here to our sampling distribution, this is when we would repeatedly take samples, all of the same size, and then whatever we would get, like p hat is 40, p hat is 55, we would come over here and we would be plotting the p hat values. Notice that that's what my x-axis is labeled as there. And so you can almost picture that each of the dots that would be in the dot plot is representing, you know, basically a p hat, or a sample proportion. Okay, so a really key distinction here is when we're talking about a sampling distribution, this consists of taking all of the possible simple random samples that you could draw out of size 20, and then you are calculating a statistic, a sample mean or a sample proportion, and then this graphical display here is describing all the many repeated p hats or x bars that you would get. Okay, and you can see there's another graphic down here at the bottom. It's that same idea. Here's my population. I'm drawing out repeated samples, all of the same size. On this one, maybe I'm calculating the sample mean, so the x bar from each of those. Okay, and then I would use those to kind of help me build what my sampling distribution is. Okay, and in that scenario, you can picture the x bars would then be acting almost as the dots that you would be creating in your dot plot there. Okay, so on the next page here, just making sure that we're clear with what the difference is between a population distribution and a sampling distribution. And in fact, there are actually 3 different distributions that we had just reviewed there on the front. Okay, just keeping straight each of these 3 things, particularly with a sampling distribution. A true sampling distribution is when we've taken all the possible samples of the same size. That's really extremely difficult, but that's why we usually just call what we are building approximate sampling distributions. Okay, it is very important that you are not interchanging these 3 terms there. They mean something very different from one another. Okay, on to this graphic. This does a really great job of kind of differentiating here between the difference between bias and variability. Okay, variability is actually talking about spread. Okay, we talked about bias first when we talked about different sampling methods in chapter 4. We said you have to make sure that you're using a proper random sampling technique so that you don't introduce bias into your results. Okay, and here we have 4 different bullseyes here, and I think what we want to make sure that we are keeping straight here is when we're talking about bias. Okay, when we're talking about bias, this is when we are consistently missing the target, but we don't stop there. It has to be consistently missing the target. By the way, for us, the target would be trying to figure out where that true parameter is of the population, whether it's the mu or whether it's the p, the population proportion, but it's consistently missing that. This is important, in the same direction. Okay, so it's always overestimating your mu, or it's always underestimating mu. Okay, so when we talk about bias, we're referring to accuracy. Okay, it's talking about our aim is off, always in the same direction. And so as you look at these 4 bullseyes here, and you can just picture that the target would be where that population parameter is. I have a mu there in each of those. You can see that in these scenarios on the left, there is very high bias, because you can tell that we are consistently missing the target. We're up here in the top right of our target here, and we're missing the bullseye pretty consistently in the same area. Okay, versus what variability is referring to, that's describing how spread out. Okay, so this is referring to if you were to take repeated shots and they're kind of widely scattered on the target. Okay, this is referring to actually precision. Okay, and so you can see the 2 pictures over here on the right. These 2 pictures are are actually showing, oh, I'm sorry, I should be talking about bias here. Okay, just the two pictures on the right both have a very low bias, okay, a low bias. Even though this one in the top right corner seems to have a lot of spread and variability, you'll notice that this is still centered at that bullseye. So the bias, I had some that were over here, over here, over here. It's not consistently missing the bullseye in the same direction like these ones on the left are. Still, the center is pretty much the very middle there of the bullseye. And obviously here, we were really very centered quite well. Okay, so low bias on these, high bias on those. In regards to the variability, okay, the high variability is happening in each of these two pictures. You see there's a lot of spread, and there's low variability in these two. We had a lot more precision taking place there. Okay, now here's kind of how all of this ties together. The great thing about a sampling distribution here is it really helps you locate the center of your population. Okay, if you were to take a statistic and it's considered an unbiased estimator, that means it's not missing the target in one consistent direction, but it's actually kind of centered right at the parameter. Anytime you have constructed a sampling distribution, the center of your sampling distribution should be spot on with what the center of the population is, okay? Which is a really, really awesome thing, and we kind of uncovered that a little bit with the Reaching for the Beads activity. Okay, the other really important aspect to look at is the spread. Okay, we know spread is referring to variability, okay? And I think the key thing that we want to make sure that we're understanding is how spread out your sampling distribution has everything to do with your sample size. So if you're taking larger samples, what that's going to result in is that's going to result in your sampling distribution shrinking in size. It's not going to span as much, which is great. We don't want there to be a lot of variability. We want it to kind of really center in on what we're thinking the true parameter is. And so you can see in this example here on the left, I guess it doesn't tell you what the sample size is on this one over here on the left, but over here we're now in, oh yeah, it does. No, it doesn't. Okay. The sample size of the one on the right, anyhow, is 1,000. And so you can see that apparently this one pictured on the left, the sample size was much smaller. Maybe they were drawing out sample sizes of, we'll just say, size 100. Okay, and you can see that while it does still feel like it's centered maybe somewhere around 0.37, so we have a hunch that maybe 37% is what the true population proportion was. You see that there's still quite a bit of variability. It's spanning from, a p hat that was 0.22 all the way up to a p hat that was 0.52. But if you change your sample size and now you're drawing out samples of 1,000 and you make a sampling distribution of that, you'll notice that it still feels like it's centered at 0.37, but with a lot less variability. Now our smallest p hat was 0.31 and the biggest was 43% there. Okay, so let's take a look at the shape here. Okay, shapes of sampling distributions. Okay, it mentions here that they can take on many different shapes. The same statistic can have sampling distributions with different shapes. We're going to assume that what we're looking at here, the parameter of the population, we'll say this is a mean weight here, mu, is 80 pounds. Okay, so I have sampling distributions of 4 different statistics here, and I'm just going to kind of highlight right up through where 80 is. Okay. Now the first question is, which of these statistics, okay, and I'm talking about here's stat 1, 2, 3, and 4. Okay, which of those appear to be a biased estimator? Okay, now remember, biased means it's consistently overestimating or it's consistently underestimating where that true population parameter is actually located. Okay, so as we take a look at this, Okay, as we take a look at this here, it kind of feels like, well, maybe the second stat, this graph, see how the majority of these dots are falling to the left of where 80 is? I probably could suggest that stat 2 is looking like it's a biased estimator, and it sort of feels like that would be underestimating, for the most part, where the true population mean weight is of 80 pounds. The other one that looks like maybe it's a biased estimator could be stat 4, because I see a lot more dots on the right than I do on the left. Stat 1 and 2 kind of feel like maybe I have about the equal amount of dots there. So I'm also going to call stat 4 as maybe slightly overestimating my population parameter. Now the next one says, of the unbiased estimators, so now that's talking about stat 1 and 3, which one do we think would be the best one to use? Okay, well, anything that has less variability, less spread is always better. So even though 80 is maybe roughly the center of stat 1 and roughly the center of stat 3, because stat 3 only spans from maybe about 72 to 89, and stat 1 goes from 50 up to maybe roughly 97, it would be much, much better to choose stat 3. Okay, so we're going to say stat 3, and our reason is going to be because there is less variability. Okay, there is less variability with that. Okay. All right, and then on our last page here, just a few things that I just want to highlight here, because these are super important. If we are increasing our sample size, okay, increasing your sample size will actually decrease the variability in your sampling distribution. Okay, it will not make the spread near as much. You can see this in an example down here where I think when Donald Trump was running for president the first time, they were asking individuals if they thought that he was the best presidential candidate to come along in the last century. And then so people were either responding yes or no, and then they were recording which proportion what proportion out of that sample said that he was the best presidential candidate to come along in the last century. Okay, now what I want to draw your attention to is the sampling distribution that you're shown at the top is sample sizes of 100. The sampling distribution that you're shown here at the bottom is a sample size of 300. Okay, notice in both of these instances, it feels like maybe we're centered around the 75%, which actually it alluded to this here when it mentioned we're going to suppose that this is the true population proportion, that 75% of the students in this school felt like Donald Trump is the best presidential candidate. Okay, and you'll notice they're both centered. So these are both really good unbiased estimators, but look at what happened when our sample size went up. You can see that the variability or the spread really started to shrink there. Okay, so last couple things here, just mentioning, if you were to take a larger sample size, it absolutely will reduce your variability, but a larger sample size will never repair your bias. If you have bias where it's consistently over or consistently underestimating your population parameter, the only way that you can fix this is to go back and take a sample again and make sure that you are using proper sampling techniques. If you're not using good sampling procedures, you will introduce bias into your results. And so you really have to start all the way back at square one and regather your data in a proper way to fix the bias situation. You can't just say, well, let me just survey more people. Let me just survey more and see if I can get it to balance. That's not the way to fix bias there. Okay, there's a few problems there for you.